I'm ready to get started. I have this tendency to sing. I don't know why. I guess I like to sing. Good morning. Today we are going to review everything I think you should memorize for the AP Physics C Electricity and Magnetism exam.
Flippin' Physics.
I thought Mr. P was vehemently against rote memorization.
He is.
But sometimes it is helpful to memorize things.
Like for a big exam.
Like the AP Physics C Electricity and Magnetism exam.
Okay, sure. I guess that makes sense.
Yeah, so there are a lot of equations and information provided to you on the exam. However, I'm going to highlight things which I think you need to remember, which are not included on the equation sheet or in the table of information. For example, charge capital Q equals number of charge carriers lowercase n times the elementary charge lowercase e. This is the equation which shows that charge is quantized. Charge comes in discrete quantities in intervals of the elementary charge. The charge on a proton, or the absolute value of the charge on the electron, 1.6 times 10 to the negative 19 coulombs.
We have to memorize that the number for elementary charge is 1.60 times 10 to the negative 19 coulombs?
Oh, no, sorry. The number for that constant and many other constants are on the provided table of information, but you should be familiar with all the information on the equation sheet and the table of information which are provided to you on the exam.
Okay, yeah, that makes sense, thanks.
Next, Billy, what is the law of charges?
The law of charges is that two charges with opposite signs attract one another, and two charges with the same sign repel one another.
So, we're just making a list of things Mr. P thinks we should memorize. Isn't the law of charges a little rudimentary?
Well, you are correct that we are making a list of things I think you should memorize. And yes, I do agree that the fact that opposite sign charges attract one another and same sign charges repel one another is a bit elementary. However, you might be surprised at the number of times you are going to use that basic concept on the exam.
I hear you, Mr. P. Thanks.
The electric field around a point charge. Bo, please derive it.
Sure. Actually, not to be overly contrarian, however, I thought we were just listing things you thought we should memorize. Why would I derive something when we're doing that?
Oh yeah, Bo, my not too overly contrarian student. My point here is that the derivation is simple, and remembering the simple derivation will help you remember the equation, which is better than rote memorization. So, Bo, please derive the equation for the electric field around a point charge.
Sure. Electric field equals electrostatic force divided by the charge of the test charge. Okay, that means we need the equation for the electrostatic force, or Coulomb's law. Electrostatic force equals the Coulomb constant times charge 1 times charge 2 all over the square of r, which is the distance between the centers of charge of the two charges. When we substitute that expression into the equation to get the electric field around a point charge, we need to use for charge 1, lowercase q, the charge on the test charge, and for charge 2, uppercase Q, the charge on the point charge. That means r is the distance between the centers of charge of the test charge and the point charge. The charge on the test charge cancels out, and we are left with the electric field around a point charge equals the Coulomb constant times the charge on the point charge all over the square of r. And r is now the distance between the point charge and the location of the test charge. And I guess I should point out that the test charge is always positive, which means the direction of the electric field is always in the direction a positive test charge would experience an electrostatic force. Okay, I can see how understanding the derivation makes it easier to remember the equation. Thanks.
You are welcome, Bo. I want to point out that the fact that the Coulomb constant, lowercase k, equals 1 over the quantity 4 pi times vacuum permittivity seems to come up quite a bit on the exam. Yes, the equation is on the table of information. However, I thought it was important enough to make sure you remember that. Billy, please derive the equation we use to determine the electric field caused by a continuous charge distribution.
Absolutely. Well, a continuous charge distribution is a collection of point charges organized into a shape. So we need to start with the equation for the electric field around a point charge, which Bo derived. However, we need to use the vector version of that equation, which means we add unit vector r to the equation. And instead of electric field E and point charge Q, we have infinitesimally small versions of those, dE and dQ. And now we can integrate both sides. The integral of 1 with respect to electric field is the electric field caused by the continuous charge distribution. And the Coulomb constant is constant, so that can come out from the integral. And we have the equation we use to determine the electric field caused by a continuous charge distribution. It equals the Coulomb constant times the integral with respect to charge of the multiplicative inverse of the square of r, the distance between the location of the infinitesimally small charge dq and the location where we are determining the electric field, all times unit vector r.
Thank you, Billy. Bobby, please tell me the equations for all three charge densities and their units.
Linear charge density lambda equals charge over length, and the units are coulombs per meter. Surface charge density sigma equals charge over area, and the units are coulombs per meter squared. Volumetric charge density rho equals charge over volume, and the units are coulombs per meter cubed. Actually, those are only for uniform objects. If the objects are non-uniform, then we need to use infinitesimal versions of each of those variables. In other words, infinitesimal charge dq for charge q, dl for l, dA for a, and dV for v.
Thanks, Bobby. When you look at the equation for Gauss's law on the equation sheet, it says the closed surface integral of the dot product of the electric field and dA, which all equals charge divided by vacuum permittivity. I consider this equation to be missing two key pieces. One, this is the equation for electric flux. So on the left, there should be a capital phi with a capital E subscript to indicate it equals electric flux. Two, the charge on the right-hand side of the equation should have a subscript which indicates which charge we are talking about. I usually use the word enclosed because this charge is the charge enclosed by the Gaussian surface we are integrating the integral over. And if the net charge inside a closed Gaussian surface is 0, then the net electric flux through the closed Gaussian surface is also 0. And as long as we are talking about electric flux, I will point out that the equation for electric flux for a flat surface in a uniform electric field is electric flux equals the dot product of electric field and the area, or electric field times area times the cosine of the angle between the direction of the electric field and the area vector. And as long as we are talking about uniform electric fields, Bo, please determine the equation for the electric potential difference across a uniform electric field.
Sure. The equation for electric potential difference on the equation sheet is electric potential difference equals the negative of the integral of the dot product of electric field and dr. Let's identify two random points in the electric field as point A and point B. Actually, to make this easy, let's line up points A and B such that the distance d between them is parallel to the electric field. We can use electric field times cosine of theta times dr in the integral, and we know the angle between the direction of the electric field and the infinitesimal displacement dr is always 0 along distance d. The cosine of 0 is 1. The electric field is uniform over the distance and can be taken out from the integral. Therefore, the electric potential difference across a uniform electric field equals the negative of the electric field times distance d, and distance d needs to be in the direction of the electric field.
But the electric potential difference would be the same from point A to any point along the equipotential line which passes through point B and is perpendicular to the electric field, right?
True, but the magnitude of the electric potential difference is calculated using the distance d, which is parallel to the electric field.
Yeah, right, okay.
Thank you, Bo. Looking at the equations on the equation sheet for the energy stored in the electric field of a capacitor, we have 1/2 charge times electric potential difference and 1/2 capacitance times electric potential difference squared. What we don't have is charge squared over the quantity 2 times capacitance. Now, I know it is easy to derive that last expression given that electric potential difference across a capacitor equals charge over capacitance. But it is still good to remember that there is a third expression for the charge stored in the electric field of a capacitor. And when you look at the equation on the equation sheet for electric power, they only have it equal to current times electric potential difference. We know electric power also equals current squared times resistance and electric potential difference squared over resistance. Again, these are easy to derive given that we know current equals electric potential difference over resistance. However, it is still helpful to remember there are 3 different expressions for electric power.
Mr. P,
Yes, Billy?
I feel like you have not explained why you are suggesting we memorize all of these equations. I mean, why are you suggesting that?
That's a fair question, Billy. I think it mostly comes down to the dearth of available time on the AP exams.
Dearth?
A scarcity or lack of something.
Okay. Dearth.
Because of the paucity of time on the AP exams, having access in your brain to these equations can help reduce the amount of time it takes for you to solve problems, especially multiple choice problems. For example, knowing that electric power also equals current squared times resistance may require you to do fewer steps when solving a multiple choice problem. Knowing the equation for electric potential difference across a uniform electric field may also save you time. Being more efficient with your time on AP exams can increase your score, and sadly, one of your main goals when taking an AP exam is a better score.
Why? Sadly.
I think Mr. P is more concerned about our learning and our mental and emotional health than our AP scores.
Yeah.
Yeah. Anyway. Billy, please talk about what happens when we add resistors and capacitors in series and parallel to circuits.
Certainly. When we add a resistor in series, the equivalent resistance increases, and when we add a resistor in parallel, the equivalent resistance decreases. When we add a capacitor in series, the equivalent capacitance decreases, and when we add a capacitor in parallel, the equivalent capacitance increases.
You can actually see that from the equations which are on the equation sheet.
That is true, which means you can always use the equation sheet to confirm that you are remembering correctly.
Sure.
But it does come up often enough that I think having it memorized is also helpful. Now, none of the equations for resistor capacitor or inductor resistor circuits are on the equation sheet. However, I do not recommend that you memorize those equations. Instead, what I recommend is that you know how to find their limits, know the general shapes of their equations, memorize their time constants, and memorize that one time constant represents the time it takes for a 63.2% change. Bobby, please talk about all of that.
All of that?
All of that. I would suggest you start with charging a capacitor through a resistor in an RC circuit and how to find its limits.
Okay. To find the limits of charging a capacitor through a resistor, start with Kirchhoff's loop rule starting in the lower right-hand corner. The electrical potential difference around a loop equals 0, which equals the EMF across the battery minus the electric potential difference across the capacitor minus the electric potential difference across the resistor. Solving for EMF and substituting in equations gives us that EMF equals charge over capacitance plus current times resistance. For the limits, we know the initial charge of the capacitor is 0 because we are charging the capacitor. Then from the loop rule equation, we get that the initial current in the circuit equals EMF over resistance. We also know the final current in the circuit will be 0 because the capacitor will be fully charged. Also from the loop rule equation, we get charge final equals EMF times capacitance. Those are the limits. We know the general shape of the equation for charge as a function of time is y equals 1 minus e to the power negative x. That means charge as a function of time equals the maximum value for charge, which is EMF times capacitance times the quantity 1 minus e to the power negative time over time constant. But you had us memorize that the time constant for an RC circuit is resistance times capacitance. That means we can replace the time constant with resistance times capacitance. And we know that the equation for current as a function of time has the general shape of the equation y equals e to the power negative x. that means the equation for current as a function of time, which equals the derivative of charge with respect to time, equals the maximum current, or EMF over resistance, times e to the power negative time over resistance times capacitance. So for charging a capacitor through a resistor in an RC circuit, I found the limits, showed the general shapes, identified the time constant, which I have memorized, but I forgot about memorizing that one time constant represents the time for a 63.2% change. But actually, we do not have to memorize that because we know the general shape of the charge formula is 1 minus e to the power negative x. And if we plug the time constant in for time, that expression is e to the power negative 1. And we can use our calculator to calculate that 1 minus e to the power negative 1 equals 0.632, which shows us that one time constant represents the time for a 63.2% change.
Very well done, Bobby. Thanks. Now, the equations for an LR circuit are very similar, which means we could do the same thing for an LR circuit. However, let's not take the time to do that now.
Can I please do it, Mr. P?
You really want to?
Absolutely.
Okay, just do it as quickly as you can, please.
Challenge accepted.
Good luck.
Starting with an inductor capacitor circuit with zero current in the circuit, we use Kirchhoff's loop rule starting in the lower left-hand corner of the circuit. The electric potential difference around a loop equals 0, which equals the EMF across the battery, minus the electric potential difference across the resistor, minus the electric potential difference across the inductor. Solving for the EMF and substituting an equation gives us that the EMF equals current times the resistance plus inductance times the time rate of change of current. For the limits, we know the initial current in the circuit equals 0 because there was no current through the circuit before the switch was closed, and the inductor opposes changes in current. From the loop rule equation, we get that the initial time rate of change of current equals EMF divided by inductance. We also know the final time rate of change of current will be 0 because the current will be at its maximum value. From the loop rule equation, we get current final equals EMF over resistance. You asked us to memorize that the time constant for an LR circuit equals inductance divided by resistance. We know the general shape of the equation for current as a function of time is y equals 1 minus e to the power negative x. That means current as a function of time equals the maximum value for current, which is EMF divided by resistance times the quantity 1 minus e to the power negative time over time constant, or negative resistance times time divided by inductance. And we know that the equation for the time rate of change of current as a function of time has the general shape of the equation y equals e to the power negative x. That means the equation for the time rate of change of current as a function of time equals the maximum time rate of change of current, or EMF divided by inductance, times e to the power negative resistance times time over inductance. So for an inductor resistor circuit with 0 initial current, I found the limits, showed the general shapes, identified the time constant which I have memorized. I do not need to discuss the fact that one time constant represents the time for a 63.2% change because that would be redundantly redundant because Bobby already talked about that.
Nice.
Was that quick enough for you, Mr. P?
Yes, Billy, it was. Thank you.
You are welcome.
Next, I want to point out that while Ampere's law is on the equation sheet, it does not identify that the current is the current inside the Amperian loop, and I think it should.
And the equation sheet uses the variable dl instead of ds like you do.
Sure, but that does not matter much. I think it is helpful to have an equation for motional EMF memorized. Motional EMF equals velocity times magnetic field times conductor length. But of course, you also need to be able to derive that equation using two different approaches.
And that motional EMF equation assumes the velocity of the conductor and the magnetic field it is moving through are normal to one another.
Right. But what is the equation for the inductance of an ideal solenoid?
The inductance of an ideal solenoid equals mu naught, the magnetic permeability of free space, times the square of capital N, the number of turns in the solenoid, times capital A, the cross-sectional area of the solenoid, all over curly L, the length of the solenoid. And I guess we should point out that if the solenoid has a material inside its core, then the magnetic permeability of free space is replaced with the magnetic permeability of the core material.
Right. This helps you remember that the inductance of an ideal solenoid depends on the number of turns, cross-sectional area, solenoid length, and the magnetic permeability of whatever is inside the core of the solenoid. And inductance does not depend on the current through the solenoid.
Resistance does not depend on current either.
And capacitance does not depend on charge on the plates or electric potential difference across the plates.
Correct, Billy and Bobby. Realize, of course, you also need to be able to derive the equation for the inductance of an ideal solenoid.
Of course.
And lastly, LC circuits. Bobby, tell me what we need to have memorized about inductor-capacitor circuits.
For inductor-capacitor circuits, we need to have memorized that they are in simple harmonic motion. Energy oscillates back and forth between electric potential energy stored in the electric field of the capacitor and magnetic potential energy stored in the magnetic field of the inductor. The angular frequency of an LC circuit equals the multiplicative inverse of the square root of inductance times capacitance. Angular frequency of simple harmonic motion equals 2 pi times frequency, which equals 2 pi divided by period. So the period of an inductor-capacitor circuit equals 2 pi times the square root of inductance times capacitance. And of course, we have to be able to derive the equation which proves inductor-capacitor circuits are in simple harmonic motion. Right, Mr. P?
Correct, Bobby. In fact, I would suggest you know how to derive everything we have learned in our lessons about AP Physics C, electricity, and magnetism. Best of luck to each and every one of you taking the exam. And honestly, even those not taking the exam, it's really a fun and challenging curriculum. Thank you very much for learning with me today. I enjoy learning with you.